Welcome to this presentation on the flow across a normal shock and how we can analyze that. If you want to check out the handout that goes with this, the link is in the description for the video. And getting into it here. Here's where we're at in the forest of topics that we're going to be covering here. Compressible flow is the last piece of power systems. It follows along from gas power systems. It could be a topic in its own right, but that's kind of how we're fitting it in here. So last time we talked about the converging-diverging nozzle and how as the back pressure drops, right, as the back pressure goes down. Now, if you haven't seen the video, please go watch that because it doesn't make a lot more sense as I talk through this. But as the back pressure goes down, we can see the flow can go through the nozzle more quickly with a constant upstream pressure. And as it goes down, we eventually get to a point where it's going to be sonic at the throat. And if we go further, we're going to continue to remain sonic at the throat, but we continue into the supersonic velocity cases, so Mach number greater than 1. But then we get these shocks that can occur inside the nozzle. Right? So we get a normal shock here if the pressure gets lower, and then maybe even a shock here at the exit. And what we want to do today is analyze how do we do the analysis in our nozzle across those shocks, because a lot of things are changing across a normal shock, and so far we don't have the knowledge of what to do as we go across that shock. So that's what we're going to look at today. All right, here's an image of a normal shock. So this is you can see it's converging here a bit. Mach number upstream is 1.3, and then we're going to have some Mach number downstream, which we'll actually look at in a little bit. Overall, it's obviously very, very thin, on the order of millimeters. Actually, maybe less than that, 10 to the minus 5 centimeters in width. Obviously, it depends on what kind of shock you're dealing with, but obviously very, very small scale. These disturbances we see here and here, this is just due to the flow separation and the boundary layer that's occurring as the flow is going through this duct/pipe type shape. All right. So let's look at what kind of analysis we can have here. So across the normal shock, we've got a couple different things. We're going to have kind of the X side here, and we're going to have the Y side. That's downstream of the shock. Downstream of the shock is Y. Upstream of the shock is X. All right, so we have some velocities, Mach number, temperature, pressure, enthalpy, entropy, and likewise downstream. All right, so we're going to kind of see the comparison. So you can see here we're looking at mass first. And a mass, you can just think we'll look at mass flow rate. So we start by looking at mass here, and you can think of mass in the process here would be mass flow rate is what we want to consider. So the mass flow rate on the X side is going to be equal to the mass flow rate on the Y side. Conservation of mass, hopefully it's not a surprise at all. Another way we could write this is we could have the density on the upstream side times the velocity on the upstream side is equal to density on the downstream times the velocity on the downstream side. All right. Next one is energy. So energy, if we do an energy bounce across our normal shock, we'd have some enthalpy upstream and plus obviously some velocity, right, squared over 2. And on the downstream side, we're going to have some enthalpy Y plus its velocity in the Y squared over 2. Right? And so what you can probably see here then is if we look at the stagnation enthalpy, or H naught sub X, it's going to be equal to the stagnation enthalpy on the Y side. Right, so the stagnation enthalpies are actually the same. Stagnation enthalpy is the same the whole way through our nozzle. Now let's keep going here. Momentum. All right, so if we did a momentum analysis, we'd have some pressure upstream acting on our control volume, some pressure downstream acting upstream on our control volume, and then obviously the momentum change through our control volume. So that would end up being, we have the area of the control volume, cross-sectional area, times the pressure on the upstream side minus the pressure on the downstream side. So that would be the forces acting on the control volume. It's going to be equal to the mass flow rate times the velocity on the downstream side minus the velocity on the upstream side as our momentum change. All right, so the net pressure force is equal to the net rate of momentum change. All right, so that's the momentum analysis. Entropy. For entropy analysis, we're going to say we got entropy is on the Y side minus entropy, on the downstream side minus the entropy on the upstream side is got to be greater than or equal to 0. So more than likely it's not an isentropic case. It does say it could be equal to 0, but we are creating some entropy here in this process of going across this normal shock. All right, last one we're going to look at is the area ratio versus the stagnation pressure ratio, and you'll see why in a bit because we'll use this often from the table. Be helpful for us. But if we the area ratio is the area on the upstream side, and it's not just the area of the shock, it's the area of the throat, or where the Mach number will be equal to 1 on the upstream side, divided by the area of a place where you had Mach number equal to 1, or where there would be a throat on the upstream side. So it's kind of hypothetical. It doesn't necessarily have to be a throat on both sides, but what would the area be if there was a throat where the Mach number was 1 on either side of our shock? All right, and that's going to be equal to our pressure, stagnation pressure on the downstream side divided by the pressure, stagnation pressure on the upstream side. All right. As you can probably see, you can carry this out. This could also be written as, so you have the stagnation pressure on the upstream side times the area on the upstream side equals the stagnation pressure on the downstream side times the area of our throat on the downstream side. All right, so all those things are going to come together to help us do the analysis across the normal shock. So where are the values? What's the calculations we need to do? Well, the calculations are, you can find in a typical book or look up into compressible flow. Just going from the table is pretty easy. This really just becomes a little bit of a strategy of how we can solve across the normal shock to figure out different properties, like we have already for the converging-diverging nozzle or just the converging nozzle. But what you can see here is we have the Mach number upstream, Mach number downstream, and then we have the pressure just up and just downstream ratio of across the shock. So this is the pressure just on the Y on the downstream side divided by the pressure just on the upstream side. So not stagnation, because that's over here. Here's stagnation pressure on the downstream versus the upstream side. And again, we also have the temperature at the shock on the downstream side versus the upstream side. All right. The thing to note about this, actually going back to the picture if we wanted to, so the picture we had 1.3 on the upstream side. So what was the Mach number on the downstream side of that picture? It would be 0.78596. All right, if we want to figure out what the pressure ratio was, we can look right here for this given Mach number upstream. And so basically we need to do a little bit of be creative in how we figure things out, and that's what we'll do when we look at the example in class. So I hope this was helpful. If you have any questions, feel free to put them in the questions or comments below the video, and hope to see you for the next video. Thanks.